As a next example, I want to prove the following. All right, so I want to show that the sequence Sn equal to -1 to the n, that this sequence does not converge, as we asserted in the beginning when I gave you examples of sequences. All right, let's suppose in the quantity that it does. And it does converge to something, so that the limit as n goes to infinity of -1 to the n is equal to some number L. Okay, so then, by definition of the limit, for any epsilon greater than 0, there exists a capital N in R such that n greater than capital N would imply that Sn, in this case Sn is -1 to the n, so let's replace it by that, -1 to the n minus L, that this would be less than epsilon. All right, so with this in mind, then, let's see, we have two choices. So there are odd n such that -1 to the n minus L is less than epsilon, right? Because, in fact, let me just add it here, not just odd n, but odd n greater than capital N. Because above any number I have both odd numbers and even numbers. And then I can take advantage of the fact that I know what -1 to the odd power is. This would be -1 to the odd power is -1. So -1 minus L is less than epsilon. And then I can factor out minus, and after I take absolute value, minus will disappear. So this is the same thing as saying L plus 1 should be less than epsilon. Also, in fact, let's copy all of this. And make this first statement part 1. And part 2, if there are odd numbers like that, there are also even numbers like this, right? So there are even numbers such that -1 to the n minus L is less than epsilon, and -1 to an even power is going to be just 1. So for even numbers we have this. and then 1 minus L or L minus 1 is the same thing. So then what we got out of these two statements is this. So therefore L minus 1 should be less than epsilon, and L plus 1, absolute value, also should be less than epsilon. Okay, that means that actually the distance between L and 1 is less than epsilon, right? That's the first statement. And the second statement says that the distance between L and minus 1 is less than epsilon. Well, but if that is the case, then the distance between 1 and minus 1 should be less than 2 epsilon, right? So indeed, what can we say here is this. What's the distance between 1 and minus 1? It's absolute value of 1 minus 1, which is in fact 2. That's not really very surprising. And now I can play the same trick as I did in one of my previous examples when I was showing uniqueness of a limit. I can take what I've written here and I can add and subtract L. So 1 minus L plus L, and minus 1 is really plus 1. Right? So adding and subtracting L really does not change anything. But then by the triangle inequality, I'm going to get that this is less or equal than absolute value of 1 minus L plus absolute value of L plus 1. And of course, I'm free to interchange 1 and L in a difference, because when I take absolute value of the positive number or negative number is the same thing. So magnitude of L minus 1 plus magnitude of L plus 1 is how I can write this statement. But then I already know that both L minus 1 and L plus 1 in absolute value must be less than epsilon. So this is going to be less than epsilon plus another epsilon equal to 2 epsilon. Okay? So the conclusion from this is, if I follow this chain of inequalities, is that 2 must be less than 2 epsilon. And not only it must be less than 2 epsilon, but my original statement was for any epsilon, right? So that means that what I have found here is that this is true for any epsilon greater than 0. Right, and this is clearly false. For example, I can take epsilon equal to 1/2. Right, because if epsilon is equal to 1/2, then I'm going to get 2 is less than 1, which is a contradiction. So we got a contradiction. And that means that our original assumption that the limit of minus 1 to the n is equal to L is false. So the limit as n goes to infinity of minus 1 to the n, this guy does not exist. All right. So next example is going to be example 5 from the book. That would be one of the two important examples to review. So let's do the following. So suppose that Sn is a sequence of non-negative numbers. Non-negative real numbers, such that the limit n goes to infinity of Sn is equal to S. What we want to do is to prove that the limit Sn goes to infinity of square root of Sn, not surprisingly, must be equal to square root of S. Now, the difference between this problem and the other problems that I have done so far is this, that for previous problems, like when I was computing the limit of 1 over n, I dealt with Sn, for which I knew what the equation for Sn is, so it was easy for me to find capital N's to fit the definition. In this case, I'm just given that Sn is some non-negative sequence about which I know that it converges. So any n that I'm going to use in this case, capital N, I will not be able to determine explicitly, so I'll have to use other information to deduce that a capital N for a given epsilon would exist. Okay, so let's consider in this case several cases. Case number one is this. So if I know that I have a positive sequence or non-negative sequence, what can I say about the number S, the limit of that sequence? Can this number be, for example, negative? Because if it is negative, then what I'm writing here is going to be invalid. Okay, so number one, I want to show that S is going to be greater or equal than 0. How can I show that? In exactly the same way as I just did in the previous example of minus 1 to the n. I'm going to suppose, on the contrary, that S is equal to some A, and A is less than 0. Okay? All right, so then, by definition of a limit, for any epsilon greater than 0, there exists a capital N in R such that n bigger than capital N would imply that Sn minus, so the limit is A, minus A is less than epsilon. So, all right. Okay, so Sn is a positive number. A is a negative number. In fact, to make our life simpler, let's say, this. Well, actually, let's not say anything. So A is just a negative number. Okay, so then if I look at Sn minus A, is there anything that I can say about it? So Sn is positive, A is negative. So then if I drop Sn out of the picture, and I just take absolute value of minus a, that is going to be less than absolute value of Sn minus a, right? Because if I take a positive number, I subtract a negative number. If there is no positive number, then of course the absolute value is going to be, of a difference is going to be smaller. So then absolute value of a is going to be less than absolute, less or equal, because Sn is allowed to be 0. Less or equal than Sn minus a absolute value, and this is less than epsilon. And this should be true, again, for any epsilon greater than 0. Well, but then this is going to give me a contradiction, right? So contradiction. Just take epsilon to be absolute value of a over 2, right? Because in that case, absolute value of a is going to be less than absolute value of a over 2, and that's impossible. So the conclusion is that S must be greater or equal than 0. Okay? So again, what I used here is the fact that I can drop Sn from this inequality, and absolute value of Sn minus a is always going to be bigger than a, because Sn is positive and a is negative. Okay, so S is greater or equal than 0. So now let's do number 2. Suppose that S is actually equal to 0. So what does it mean? It means that the limit n goes to infinity of Sn is equal to 0. Okay, so now I want to show that the limit of square root of Sn is square root of S. So, and S is equal to 0, so now I need to show that the limit n to infinity of square root of Sn is going to be equal to 0. Okay, so the way I'm going to do this is going to be as follows. I want to fit the definition of the limit. So I'm going to choose any epsilon greater than 0. And what I want to determine capital N, for which square root of Sn minus 0 is less than epsilon, right? So that's what I want. Well, let's try to simplify this. If I'm writing an expression like that, that's the same thing as absolute value of square root of Sn less than epsilon, because 0 doesn't matter. This is the same thing as, I can drop the absolute value sign because square root of Sn is always positive. Square root of Sn is less than epsilon. And if I have two positive numbers, one of them is less than another one, then if I take square of both sides of this inequality, it should be preserved. So therefore, Sn must be less than epsilon squared. And in fact, I can follow these chain of inequalities forward and back or backward, right? If I assume that Sn is less than epsilon squared and Sn is a positive number, once I take square root, this is going to be true. This is equivalent to this, equivalent to that. Okay, so but now, would I be able to choose capital N in such a way so that I can guarantee that this is true? Well, yes, I can. By the definition, so let's write this. So by definition, of the limit limit as n goes to infinity of Sn equal to 0, there exists an n in R such that n is bigger than capital N would imply that Sn minus the limit, well, it can be less than anything I want, so in particular, I can force it to be less than epsilon squared. Saying that is actually the same thing as saying Sn is less than epsilon squared because Sn is positive, and subtracting 0 from Sn does not make a difference. Okay, so but then if Sn is less than epsilon squared, then I can follow the chain of inequalities over here, follow it backwards. To get that square root of Sn minus 0 is less than epsilon. Right? So once again, I did this scratch work here, which establishes that saying this is equivalent to saying that Sn is less than epsilon squared. Then by definition of a limit of Sn, I should be able to find capital N such that if n is bigger than capital N, then Sn is less than epsilon squared. And so then from here, it follows that this would imply that actually square root of Sn minus 0 must be less than epsilon. And so then I'm done, because for every epsilon, there exists a capital N such that square root of Sn minus 0 is less than epsilon. So the proof is complete. Notice that the thing that I mentioned in the beginning, that in this case, I cannot determine exactly what the capital N is. But the thing is that in this case, I know that the capital N for square root of Sn exists because I know by definition of a limit that a capital N exists for Sn, because I know that the limit of Sn is 0. Because the limit of Sn is 0, then for any epsilon, I know that there is a capital N. I don't know exactly what it is, but I don't care, because the only thing that I need to know is that capital N like that exists. All right, so then we have one more case remaining. That's number 3. So the only remaining case is S is positive, right? We said that S cannot be negative. We considered already the case S equal to 0, so now the only remaining case is S positive. All right, so again, let's do the scratch work first. So I'm going to choose any epsilon greater than 0. And what I want is this. I want square root of Sn minus square root of S, absolute value. I want that to be less than epsilon. So, and what I need to do is I need to reduce this inequality to something about Sn minus S, because I know the limit of Sn exists So I am able to make Sn minus S less than epsilon, but not directly square root of Sn minus square root of S. Okay, so what do we have? If I look at square root of Sn minus square root of S, what I can do is multiply and divide by the conjugate. So square root of Sn minus square root of S, square root of Sn plus square root of S. Again, remember that my goal is to make this look like Sn minus S, so I need to get rid of square roots. Divided by square root of Sn plus square root of S. What is that? Sn minus S square root of Sn plus square root of S. And here, what I can see is that in the denominator I have two numbers, square root of Sn and square root of S. And I know that both of those are positive. And I know that S is not equal to 0. So what I can do is I can drop square root of Sn from the denominator. And if I do so, the denominator will become, I'm removing a positive number from it, so denominator will become smaller, and because it becomes smaller, the fraction will become bigger. So this is less or equal, because Sn in principle can be equal to 0, than 1 over square root of S times Sn minus S. Okay, and so then from this I can immediately conclude that if I want to compute, or if I want to estimate the absolute value of the difference between square root of Sn and square root of S, by using the same inequalities, I'll have that this is less or equal than 1 over square root of S, which is a positive number, times Sn minus S. And I can make this less than epsilon if Sn minus S is less than epsilon times square root of S. Okay, so this is less than epsilon, provided that this guy is less than epsilon square root of S. Okay, so then the question is, would I be able to make this true, this circled inequality? And the answer is yes, by definition of the limit again, limit n goes to infinity of Sn equals S, and there exists a capital N in R such that as a replacement for epsilon in this definition, I can use epsilon times square root of S. So such that Sn minus S is less than epsilon square root of S. But then what have I found? Given an arbitrary epsilon greater than 0, I was able to find a capital N such that this is going to be true. But if this is true, then by following the inequalities backwards, I get that this guy is less than epsilon, and so that means that the limit of square root of Sn must be square root of S, and so once again, we're done. One more example of a similar type. Okay, so And that would be example 6 in the book, also important. So let's suppose that Sn is a sequence of real numbers such that Sn is not equal 0 for any n. And in this case, I want to prove something else. I don't want to prove anything about the limit. I want to prove something about an infimum. So if the limit as n goes to infinity of Sn is equal to S, that is itself also not equal to 0, I want to show that the infimum of Sn is greater than 0. Not Sn, but absolute value of Sn. Which means that under these assumptions, I would never expect that absolute value of Sn would ever get very close to 0. It's going to be what is called bounded away from 0. All right, so let's try to prove this. And maybe let's try to motivate this first. So if I have a number line, let's see. So let's say 0 is somewhere here. S is not equal to 0, so maybe it is a positive number. So what do we know? We know that the limit as n goes to infinity of Sn is S. So that means that eventually all Sn's are going to be in the vicinity of S, right? Close enough to S so that they stay away from 0. So that means that starting from a certain capital N, I would expect that Sn are farther away from 0, let's say, than S over 2. Well, but then before that capital N, what do I know? I know that before n is equal to capital N, I'm looking at n different numbers, capital N different numbers, S1, S2, S3, etc., as capital N, all of which are not equal to 0. So that means that their minimum is different from 0. So that means that it doesn't matter if I have a number with an index which is less than capital N or bigger than capital N, all S's would want to stay away from 0 in absolute value. Okay, so let's try to formulate this more carefully. So by definition of a limit, that's the first thing. So first I'm going to look at the case when Sn are close to S. By definition of the limit, we have that for any epsilon greater than 0, there is an n in R such that n bigger than capital N should imply Sn minus S is less than epsilon. So I'm going to choose, again, in line with this picture. If I choose epsilon to be half of a distance between s and 0, then that would ensure that the numbers that I'm going to get are going to stay s over 2 away from 0. So let's do this. Choose epsilon equal to absolute value of s divided by 2. Right? In this case, I don't know if s is positive or negative. Epsilon has to be positive, so I'm going to make it capital S, absolute value of s divided by 2. Okay, so then there exists an n in R such that n bigger than capital N implies absolute value of Sn minus s is less than absolute value of s over 2. Right? I'm just rewriting the definition of a limit for the specific choice of epsilon. Okay, now what I can do, I can try to rewrite this inequality without using the absolute value sign on the left-hand side. How can I do that? We will need actually the following statement, which I'm going to prove separately now. So let's suppose that I have my triangle inequality. So a plus b less or equal than absolute value of a plus absolute value of b. And let me make the following change. Let's say I'm going to set c to be a plus b. If c is a plus b, then b is going to be equal to c minus a. All right, so then if that is true, then my triangle inequality can be rewritten in the following form. A plus b is c, less or equal than a, plus absolute value of c minus a, right? So I'm really not doing anything, I'm just relabeling the sides in a triangle inequality. And if that is true, then if I subtract absolute value of a from both sides, then I'm going to get that absolute value of c minus a must be greater or equal than absolute value of c minus absolute value of a. All right, so with that in mind, and actually one other thing, if I interchange, so there is nothing in this case that said that I should make c, should express b in terms of c minus a. I could have expressed a as c minus b, and I will come up with exactly the same inequality, except that a will be replaced by b. So with this in mind, let's now apply it in our case. So what is Sn minus s? Let's see. So we have that absolute value of Sn minus s, well, it's greater or equal than absolute value of Sn minus absolute value of s. And likewise, it is going to be greater or equal than absolute value of S minus absolute value of Sn, right? Because I can simply interchange Sn and S in my under my absolute value sign. That doesn't change anything. And then interchanging things on the right hand side will give me this inequality, the second inequality. And so if I combine this now, so now combine the last inequality and my inequality here. Sn, so what I will have is S minus Sn is less or equal than Sn minus S. This is less than absolute value of S over 2. If n is bigger than capital N. But then if I rearrange the inequality that I just obtained, move S over 2 on to the left and Sn, absolute value of Sn, on the right, what I'm going to get is that absolute value of Sn is strictly greater than is greater than absolute value of S over 2 if n is bigger than capital N. Okay, so once again, from a definition of a limit and using epsilon equal to absolute value of S over 2, we're going to get this circled inequality. Then triangle inequality can be rewritten in this way. And if a triangle inequality can be rewritten in this way, then I have two possible inequalities that result from a triangle inequality. I'm using then the second one, combining it with the inequality that I got from the definition of a limit to get this. And then simplifying that inequality, we have the following. And actually what I have established is nothing but what I promised on this picture here, right? That eventually, when n is sufficiently big, Sn is so close to S that its absolute value must be bigger than S over 2, right? So I have to stay away at least S over 2 from 0. At least absolute value of S over 2 from 0. All right. So then I can make the following assertion. So if Sn, absolute value of Sn, is bigger than absolute value of S over 2 when n is bigger than capital N, so if I consider the set Sn, n is greater than capital N, then for that set, in fact, absolute value of Sn, sorry. For that set, what I know is that every term of this set is bigger than absolute value of S over 2. So then absolute value of S over 2 is a lower bound for this set. Okay? All right, and so now I'm going to consider another set. Sn, or absolute value of Sn, n is greater or equal than 1, less or equal than capital N. This set is finite. And so its minimum exists and is equal to the minimum of absolute value is 1, absolute value is 2, etc. Absolute value of S capital N. Right? So it's just the minimum of all of these numbers. Okay, so now, finally, I'm going to consider the full set. Absolute value of Sn, where n is greater or equal than 1. All right, so what do I know? I know that starting from capital N, the elements of this set are bounded from below by absolute value of S over 2. Before capital N, before n including capital N, the minimum of the numbers from absolute value of S1 to absolute value of Sn is a lower bound on this part of the set. So now if I take a minimum of the two things, if I take a minimum of S over 2 and this minimum, then I get a number which should be smaller than any element with an index bigger than capital N or less or equal than capital N. And so that would be a lower bound on my set of all possible absolute values of Sn. So the number minimum absolute value of S over 2 minimum absolute value of S1, etc., up to the absolute value of Sn, which actually, so if I take a minimum of n numbers, like here, and then I take a minimum of a minimum and another number, S over 2, you can actually easily check that this is the same thing as saying a minimum S1, S2, etc., Sn, and I just need to include S over 2 on the list, that this number is a lower bound on this set. And one last thing that I need to know about this number is this. So this set is bounded from below. But also, let's call this number A. If I look at A, so A is a minimum of capital N plus 1 numbers. Any of these numbers, S1, S2, all the way up to Sn, none of these numbers are equal to 0 because we assume that the sequence consists of numbers which are not equal to 0. And the limit S is also not equal to 0, so this is not equal to 0. So that means that A is strictly positive. So A is strictly positive. A is greater than 0 because it is a minimum of n plus 1, capital N plus 1, positive numbers. And so that means that my set, so therefore the set Sn n greater or equal than 1 has a positive lower bound, and so therefore its greatest lower bound must also be positive. So in theorem has to be positive, and that means that we're done. All right, so next time we're going to look at other properties of sequences, actually properties that will allow us to compute limits without actually appealing to the definition every time. So we're going to prove some usable properties of limits. All right.